We are finished with multiple integration. Now we're going on to a brand new topic in multivariable calculus called vector calculus. For the most part, much of this particular topic is going to be in two dimension. So you back into single integration or just two-dimensional calculus. Okay? So the first thing that we're going to look at, we will look at vector fields. We'll look at what a vector field is, and the reason that we're doing that because later on I'm going to talk about integrating a vector field. So you need to know what a vector field is. We're going to draw it by hand, but that's all, just one we're going to do so you can see what it looks like. Okay? Right. So vector field, what is a vector field? Let D be a set in R2. A vector field on R2 is a function, capital F, that assigns to each point x, y, and d a two-dimensional vector, f of x, y. And in R3, it's a function f that assigns to each point x, y, z a three-dimensional vector, f of x, y, z. Examples of vector fields are velocity fields, gravitational fields, electric force fields. All of these are vector fields. All right, let's look at some more definitions. And this is an important definition that we will use later on, but I thought I will bring it up right now. A vector field F is said to be conservative. Very, very important word, and we're going to see that. Let me just underline this because this is very important. This very important word. Okay. A vector field F is said to be conservative if it is the gradient of some function f. So go back to whatever chapter it was, whatever lecture that was really early when we did gradients. All right, so a vector field is said to be conservative if there is a function f such that the vector field is del f. Okay, and then we'll go back to that a little later. But I want to look at an example of drawing a vector field. So the question says to describe the vector field f of xy equals negative yi plus xg. Okay, I'm going to show you how you draw this by hand. We're just going to sketch a few vectors, and then you should be able to, by looking at what is happening, deduce what a vector field really is. Okay? So basically, remember how you draw a vector field. You assign to each point a vector based on this particular function. So let us draw. Let's see how much space do I have here. Okay, so I'll draw, make it horizontal. 1, 2, 3. No, I could do it vertical. So let me draw, put up a table of values. So xy and the vector field f of xy. Okay? And as I said, I'm not going to do I'm just going to do a few points. So I'm going to look at 0, 0. I'm going to look at negative 1, 0. 1, 0, 0, 1, 0, negative 1, negative 1, 1, 1, 1, 1, negative 1, and negative 1, negative 1. So for each of these points, you write on the vector. So you find what f of xy is. All right? So a 0, 0, when you put that into the vector field equation here, you get 0. So that's just the vector 0, 0. Negative 1, 0, put it into there. Y is 0. So this is just what am I doing? Y is 0 and x is negative 1. So this is really negative j, which is really 0, negative 1. Okay? Next one, x is 1, y is 0 again, so this is just j, which is equal to 0, 1. Next one, y is 1, so this is just negative I, which is negative 1, 0. Next one, y is negative 1, so this is I, which is 1, 0. Y is 1, x is negative 1, so this is negative I minus j, which is negative 1, negative 1. 1, 1 is negative I plus j, which is negative 1, 1. 1, negative 1, when you substitute that, that is I plus j, which is 1, 1. And negative 1 is I minus j, which is 1, negative 1. Okay? So that's all that I'm going to do, and then we'll see if we can see a little pattern. So draw up your axes. Okay, I'm going to go up to 2, negative 1, negative 2, go up to 2, negative 1, negative 2. Okay, I'm going to draw my vector field in blue. Okay, so at each point, draw the vector corresponding to that point. So at 0, 0, you draw the vector 0, so there's no vector here, basically, it's just a point. At negative 1, 0, you have the vector 0, 1. So draw at negative 1, 0, draw the vector 0, 1. So that's the vector 0, 1. Negative 1, sorry. At 1, 0, now draw the vector 0, 1. At 0, 1, there, draw the vector negative 1, 0. At 0, negative 1 below there, draw the vector 1, 0. At negative 1, 1, negative 1, 1 up there, you need to draw the vector negative 1, negative 1. So negative 1, negative 1, so you do that. At 1, 1, you need to draw the vector negative 1, 1, negative 1, 1, so you do this. At, where am I? At 1, negative 1, you need to draw the vector 1, 1, so 1, 1, so you're going to do that. At negative 1, negative 1, you need to draw the vector 1, negative 1, so you do that. Okay. Now, I'm not sure if you're seeing what is happening. Just let me show you. If I had to draw the vector here at 2, 0, I'm going to have that. This one is going to do that. Do you see where I'm going? This is going to do that. Oops. Needs to be a little, and so on. So what do you see is happening here? The vector field is rotating around the origin. It's all the vectors seem to be tangent to circles with center the origin. That's what seems to be happening. Okay? So let me go back to my black. So let us describe the vector field, and we're going to say all the vectors are tangent to circles centered at the origin and get longer as we move out. Okay. So that's vector fields. Okay, so therefore when I speak about vector fields subsequently, you'll know what a vector field is. Now let us go on to line integrals. This is going very slowly today, I don't know why. Let's go on to line integrals. In other words, what are they? We're going to start integrating over curves. Now, look at what we have done before. Huh? We have integrated over rectangles, over triangles, over other plane regions. Now we're going to integrate over curves or along curves. There are two types of line integrals we'll look at. We're going to look at line integrals of functions, and we're going to look at finding line integrals of vector fields. Okay, and then you will see the applications of all of this later. Right now we're just doing some calculations, making sure you can calculate line integrals. Okay, let's start with the line integrals of functions, and these are called scalar line integrals. Definition. The line integral of the function f of x, y, z over a curve C is denoted by, okay, we need a C below here. I don't know, there must be a way to do this. I just have to find it. Of the function f of x, y, z ds. Okay, this is how we denote the how you write this derivative, or with respect to what. Denote the parametrization of the curve C. Okay, so what we're going to do is parameterize C in order to work out the line integral. Okay, so let's say the parameter is t. You parameterize it in this way. X is x of t, y is y of t, z is z of t, and t lies between a and b. And so this is the definition of the line integral. So the line integral over C, put your C again, of f of x, y, z is equal to the integral from a to b. You write the function in terms of t by basic substitution, and you multiply by the square root of the sum of the squares of the derivatives. Note, this is not partial. Do not confuse. These are not partial derivatives, right? These are just the derivatives that you know about. Okay? And how do we get this formula? Using Riemann sums, like cutting up the curve into pieces and adding it, the same thing that we have done all along. All right, so what we're going to do is to use that formula, and let's calculate some line integrals. Okay. Number one, find the integral over C of the function x plus y plus z ds, where C is the helix given by x equals cosine t, y equals sine t, z equals t, and t lies between 0 and pi. Okay, the first thing we should do is to calculate the square root of some of the squares of the derivatives. So let's find dx dt. Dx dt is minus sine t. dy dt is cosine t. dz dt is 1. So now let's find the square root of this thing, dx dt squared plus dy dt squared plus dz dt squared. So this is the square root of sine squared t plus cosine squared t plus 1, which is just square root of 2. Any questions so far? Okay, so let's set up the integral. So we're going to integrate from 0 to pi. That's the range of the parameter. Now let's rewrite our function in terms of t. So you're going to replace x, y, and z with the parameterization. So you are going to have cosine t plus sine t plus z, which is t. We need to multiply this by square root t dt. So as you can see, this is like Calc 2 integration. Okay? So let's integrate. I'm going to put the square root 2 outside, okay? Integrate that sine t minus cosine t plus a half t squared from 0 to pi. And when you work that out, you get 2 square root 2 plus square root 2 over 2 pi squared. So that's number 1. Any questions here? Okay. Next one. You are going so slowly. Okay, ready? Find the line integral, so put c, find the integral over c of the function xy to the 4th ds, where c is the right half of the circle x squared plus y squared equals 16. We need to parameterize, always do that. We need to parameterize this c. Let's draw it and see what it looks like. So it's the right half of the circle. What is the radius of that circle, please? 4. Okay, so that's negative 4, 4. Okay, so let's parameterize c. Okay, so remember when you parameterize a circle, it's always x equals r cosine theta or t, right? And y equals r sine t, right? So we parameterize it. So x equals, so in this case, r is 4 cosine t, y equals 4 sine t. And now put the values of t. What are the range of values for t? Anybody? Negative pi over 2 to pi over 2. Great. Okay? Now we are going to do the same thing again. Let's do it. Now as you can see, this question has no z. Okay? So you use the same, maybe I should write it out. The integral, let me just write it. The integral over c of f of x, y, there's no z, ds is equal to the integral, well, let's say from a to b. So you're going to replace x with x of t, y with y of t, multiply by the square root of dx dt squared plus dy dt squared dt. Okay, so I just wanted to write it again. Okay, so let's do this. We're going to find the derivatives, do the same thing we did a while ago. Dx dt equals minus 4 sine t, dy dt equals 4 cosine t. So the square root of the x dt all squared plus dy dt all squared equals the square root of 16 sine squared t plus 16 cosine squared t, which is what? Square root of 16, which is 4. Okay? Okay, now let's go and rewrite the integral. So the integral becomes the integral from minus pi over 2 to pi over 2. We write the function xy to the fourth in terms of t. So x is 4 cosine t. Y to the fourth is 4 to the fourth, whatever that is, sine to the 4t. Now we need to multiply by this 4 we just got, dt. So this is equal to, so that's 4 to the 6. Let's put that outside. From minus pi over 2 to pi over 2 of sine to the 4t cosine t dt. How do you integrate this? By substitution, good. And by substitution, and you should be able to see what this is. When you integrate this, you get 1/5 sine to the 5t from negative pi over 2 to pi over 2. And then when you substitute, when you evaluate it finally, you get 2 over 5 times 4 to the 6, which exactly is 1638.4. Okay. And as I said, you'll see the applications of all of these very soon. Number 3. Find the integral over c of x sine y ds, where c is the line segment from 0,3 to 4,6. You need to parametrize that line. Go right back to right at the beginning of this course when we did vectors, and I showed you how to find the equation of a line through 2 points in terms of t. Just let me remind you, you need to find the direction vector. Remember that? Okay? Then when you are finished, you can write the equation of the line in terms of t. Okay? So we want to find the equation of the line segment from 0,3 to 4,6. So let's go over the steps. The direction vector is equal to, so all you do, remember how to do that, you just subtract. Okay, the second minus the first, and yes, this is 4,3. And so the equation is, the first one we're going to write, remember, there are 3 ways we could have written the equation of a line segment. Remember we saw the vector equation, the parametric equations, and symmetric equations. So the parametric equations, that's what we want. So we'll use the first point, x equals 0, right, plus 40. So x equals 40. And then y equals 3 plus 3t. Now, very crucial, you now put the values for t. Now, because if you had chosen 4, 6, the values of t would be different than choosing 0, 3, okay, to write the parametric equations with the line. So tell me, so this is how you do it, and it's usually the same thing for t if you do this correctly. What value of t, right, upon substitution will give you the first point, 0, 3. So remember, the line segment, we're moving from 0, 3 to 4, 6. So the first value of t, right, would give you the point 0, 3. So 0 upon substitution will give you 0, 3. Now, what value of t will now give you 4, 6? 1. Okay, so when you put 1 into the parametric equations, you get 4, 6. Okay, so we have the range of values for t. So when you have done that, everything is the same. Let's differentiate. dx dt equals 4, dy dt equals 3. So the square root of dx dt squared plus dy dt squared equals to the square root of 16 plus 9, and that is 5. Okay, so what is the integral becoming? So you have the integral from 0 to 1, x sine t, sorry, x is 4t, sine y is 3 plus 3t, and we multiply by 5 dt. Let's simplify that. That is, now let's put 20 outside. 4 by 5 is 20. 0 to 1, we have t sine 3 plus 3t dt. Okay, we haven't done an integral like that. How do you integrate that? Any suggestions? Substitution will not work there, because if you differentiate the inner function within the parentheses, you will not get a multiple of t. The derivative of 3 plus 3t is 3. That's not a multiple of t. So, as somebody said, you use parts. If you use part, now let me do this completely because we haven't done a question with parts yet. What is u? T. Okay. And v prime is sine of 3 plus 3t. Next step. What is u prime? 1. V. I need you to integrate sine of 3 plus 3t. What is that? Negative 1/3 cosine 3 plus 3t. Good. So you apply the basic rules of integration and divide by the coefficient of t, because what is in the parentheses is a linear function. Okay? Good. Let's bring them all together now. So we're going to have 20. Let me put that 20 outside. Okay, and then you're going to have uv, which is negative 1/3 t cosine 3 plus 3t minus u prime times v. So that's a minus minus, so that's a plus, the integral from 0 to 1 of 1/3 cosine 3 plus 3t dt. Any questions so far? Okay, let's integrate. So 20, leave this negative 1/3 t cosine 3 plus 3t. Okay, integrate this for me, please. What do you get? Anybody? This one. 1/9, sine 3 plus 3t, beautiful. And we have the limits of integration 0 to 1. And when you work this out, you will get 20 over 9 times sine 6 minus 3 cosine 6 minus sine 3. Please leave all your answers like in forms like these. Don't evaluate and round off. Just leave it alone. Okay? All right. Any questions on that? So what was different about this was that you had to parameterize the line, right? By using the direction vector property, what we did way back when. And then the other thing that was different is that we use integration by parts. I think that's the first time we've used it. Okay? I would want to see the working for that, yes. Okay, so why don't you try this one? Put your c underneath that integral of y cubed. You already have the parameterization, okay, and the range of values for t, so that should not be bad at all. Okay, let's go over it. What did you get for dx dt? 3t squared. dy dt, 1. So the square root of dx dt squared plus dy dt squared is the square root of 1 plus 9t to the 4th, correct? So the integral becomes the integral from 0 to 2. Y cubed is t cubed, the square root of 1 plus 9t to the 4th dt. Did you put it into your calculator? What did you get? Let me hear what you got. Oh, that's how they give it to you. 145 times square root of 1. Yeah, that's correct. It is correct. 1 over what? 1 over 54. 3 halves minus 1. Okay, let me just do this by substitution. So I can just go over that with you again. So u equals 1 plus 9t to the 4th. du is 36t cubed dt. T cubed dt is du over 36. T is 0, implies that u is 1. T is 2, implies that u is what here? 2 to the 4th is 16 times 9 plus 1. What's that, 145? 145. U is 145. So therefore, this becomes 1 to 145, right? This is U to 149? Oh, okay. U to the half. And this is 1 over 36 du. And then you get this thing. Okay? Let me just continue here. That's u to the 3 halves. When you multiply by 2 over 3, you get 1 over 54. So you see where the 1 over 54 comes in. Okay? Any questions on that? Okay, next one. Line integrals can be used to express the total mass of a wire in terms of mass density rho. And the formula for the total mass of a wire C is the integral over C of the density, ds. Okay, so let's just do an example here. A wire in the shape of a parabola, y equals x squared, where x goes from 1 to 4, has mass density rho, which is equal to y over x. Find the total mass of the wire. Now, how do you parameterize a curve? You need to parameterize this. Okay? So it's quite simple. If you let x equals t, then y is t squared. That's all. Okay? And you do the same thing. Dx dt is 1. Dy dt is 2t. Square root of dx dt squared plus dy dt squared is the square root of 1 plus 4t squared. Okay, now let us set up the integral, right? The mass from the formula above there is the integral over c of the density y over x ds. Okay, so set up the integral. And so now let's substitute. So this becomes the integral. We forgot to put the range for t. 1 to 4 because it's right there. Thank you. So that's 1 to 4. Y over x is t squared over t times square root of 1 plus 4t squared dt, which is the integral from 1 to 4 of t square root of 1 plus 4t squared dt Okay, upon substitution, I will just give you what I got. Upon substitution, you get 1/8 times the integral from 5 to 65 of u to the half du, which is equal to 1/8 times 2/3 u to the 3 halves, 5 to 65. Which is equal to 1/12 times 65 to the 3 halves minus 5 to the 3 halves. So that's the mass. Okay. So this is just an application. Any questions? Let's look at other forms of scalar line integrals. So we're still doing that, but they can be presented in different forms. Here's one way it can be presented. The c is missing again. Evaluate the line integral over c of y dx plus 2x dy along the straight line segment C from 1, 1 to 2, 4. Okay, so there is really no difference here, but I just want to show you how you handle the way this function is written, okay? You still have to parameterize that line segment. Okay, so let's do that again. Equation of C. First, we find the direction vector. What is the direction vector? 1, 3. Now let's find the equation. X equals, so if I use the first point, 1, 1, it would be 1 plus t, y equals 1 plus 3t, and now give me the values for t. What value of t? That's the lower value, 0. And then what value of t would be the upper one would give me my second point, 1 again. Okay, it's usually the same thing if you do it correctly, right? Sweet. So you know what to do? dx. So you can either put dx, dt, or dx because it comes to the same thing there. But let's do let's do dx. So dx is 1, which is just dt, right? Right? dy is 3 dt. And all you do now, you just substitute. Okay? So you rewrite the line integral. This is a 0 to 1. So you don't use this square root thing anymore. This is just basic substitution, right? So y is, where's our y? 1 plus 3t. Good. Dx is 1 dt. We'll put the dt's afterwards. Plus 2x is 2 times 1 plus t. Dy is 3, and then you can put the dt. And all you do, you simplify this integrand. So that's 0 to 1, 1 plus 3t plus 6 plus 6t dt, which works out to be 7 plus 9t dt, which is 7t plus 9 over 2t squared, 0 to 1, which works out to be 23 over 2. Another one like that, again, it's a different form of a scalar line integral. Okay, so we're not going to use the same formula. As a matter of fact, this form is a lot easier than what we did before. Okay, evaluate, we need that c again, of x squared y dx plus x squared minus y squared dy, where c is the arc of y equals 3x squared from 0, 0 to 1, 3. It's very easy to parameterize a curve. Okay, it's very easy to parameterize a curve. Y equals 3x squared. You just let x equals t, that's all. And y equals whatever the curve is, 3t squared. Now the important thing is to put the right range of values for t. What is the lower value? What will give you the first point? 0. What will give you the second point? 1. Okay? So again, we need to find dx. Dx is just 1 dt. Dy, 6t dt. Let's make the substitution. We have the integral from 0 to 1. X squared is t squared times y, 3t squared, times dx, which is just 1, plus x squared is t squared minus 3t squared squared, 9t to the 4th, times dy, 6t dt. Okay? Now what you need to do is to simplify that. And when you simplify this, you get 0 to 1, 3t to the 4th, plus 6t cubed minus 54t to the 5 dt. Integrate 3/5 t to the 5 plus 6 over 4, which is 3/2 t to the 4th, minus 9x to the 6 from 0 to 1. And you get minus 69 over 10. Oh, why? Yeah, thanks. Sorry. Why did I put an X there? Thank you. It's a T. Okay. Now let's do one involving two line segments. Now it's the same thing. It's two line segments, you just take them separately. Okay, so you'll have you'll have two pairs of parametric equations. Okay, evaluate the integral of x squared minus y dx plus y squared plus x dy along the straight line from 0, 1 to 1, 1, and then along the straight line from 1, 1 to 1, 2. Okay, so let's take 0, 1 to 1, 1 first. And of course, you know what we need to do? We need to parameterize. Okay, so equation of line from 0, 1 to 1, 1. Okay, what is the direction vector, please? And so what are the parametric equations? X equals, let's choose the first point. X equals t and y equals just 1. And what are your values for t? What are your values for t? 0 to 1, usually. Okay? No thought necessary here. Let's do the derivatives, and then we'll... So dx is dt, dy is 0, right? So let's do that substitution right now, and then we'll deal with the other line. And then when we deal with the other line, we'll just add the two. Okay? So the integral becomes 0 to 1. Okay, what do we have? X squared, which is t squared, minus y, which is 1. Dx is dt. Now dy is 0, so that cancels out the second one, so that is just dt, which is t cubed over 3 minus t from 0 to 1. And that leaves us with negative 2/3. Okay, next line. Equation of the line segment now from 1, 1 to 1, 2. We do the same thing. Any questions before I go on to that second one? Okay. Equation of line from 1, 1 to 1, 2. Okay. We need the direction vector. 0, 1. We need the equations. Take the first point. Tell me what you get. X equals 1. Y equals 1 plus t. Range of values for t. Zero, 1. It's amazing how you always hesitate when I ask you for that, and it's always, always the same thing. Okay, let's do this. So dx is nothing, 0. Dy is just dt, right? Okay, so we're going back. So you have the integral from 0 to 1. Now note dx is 0, so the first term we don't need it. Y squared now becomes 1 plus t all squared plus x, which is 1, dy is dt. Integrate. This first term is 1/3, 1 plus t cubed plus t from 0 to 1. And then you get 10 over 3. And so you're not done yet. Your line integral is therefore the 10 over 3 minus the 2/3 you got above, which is 8/3. Any questions? Okay, your turn. Go ahead and do that one. Go over that. We need the c below that integral. Equation of c. What's the direction vector? Can somebody give me that, please? 5, 5. Can somebody give me the equations of the line? Pardon me? And y? And then give me the values of t. Don't even think. Just give them to me. Thank you so much. Okay. What is dx? And what is dy? Same thing. Substitute. So you get 0 to 1. Y squared is minus 3 plus 5t all squared. Dx is times 5 dt plus x is minus 5 plus 5t. Dy is 5t. Oh, I forgot my dt up there, did I? Okay, so when you integrate this,
dy is just 5 dt.
did I make an error? Oh, I needed, oh, sorry about that. No t, no t. So when you integrate, you will get, okay, there's a 5 here. Oops. So the integral is negative 3 plus 5t cubed. There's a 1/3. Then you divide by 5. And then this one is minus 25t plus 25 over 2t squared from 0 to 1. Final answer, please. 20? Straight? All of you got 20?
I got 385 over 6.
385 over 6? Okay, make up your mind. Which one is it? Do I have to do it?
I would take 20.
20 sounds way better.
20 sounds lovely, but 20 might be wrong. You know that, right? Okay, I'm going to do this. When you put a 1, these 5's cancel. You have a 1/3 times. When you put 1 here, this is a 5 minus 3, 2. 2 cubed, that's 8. Right? Is that right? If minus 25 plus 25 over 2. What's that? That can't be 20. 8 over 3 minus 25 plus 25 over 2. I hope I am right now. I hope you've been checking my integrals. I made an error? How what? Ay, 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 ay. I made an error. I forgot to substitute the 0. Thank you. So this is the 1. No, this first term is not going to be 0. You with me? So this is what? 1/3 times negative 27. Okay. So whatever you get, add 9. What's that? So it's 8 over 3 minus 25 plus 25 over 2 plus 9. 49 over 6?
Yeah.
Sweet. Okay. Let's move on. Good, as I thought. Line integrals of vector fields. And this is called a vector line integral. You will be seeing this quite a lot in this section. The line integral of a vector field f defined on a smooth curve C given by the vector function r of t, where t lies between a and b, is denoted by the integral over c of f dot dr. This dot is dot product. Okay? So where this is the definition for it, or the formula, it is a to b. So you write the vector field in terms of t dot r prime of t. So let me make a note of that. This dot is dot product. It's not multiplication. We're dealing with vectors now, okay? All right, let's do some examples. Let the vector field be zy squared x. Evaluate the integral, put the c, the vector line integral, where c is given by this vector function for t between 0 and 2. Okay, so the first thing we're going to find is r prime of t. So you just differentiate every component of r of t. So the first one would be 1, then e to the t, then 2t. The next thing, you want to write find f of r of t. So in other words, rewrite the vector field f in terms of r of t. So z is t squared, y squared is e to the 2t, x is t plus 1. When you have done that, find the dot product of these two. So f of rt dotted with r prime of t. So you take those two vectors. So I'm writing down everything. Dotted with 1 e to the t 2t. Remember how to find dot product. Multiply the components and add them up. So that's t squared plus e to the 3t plus t plus 1 times 2t is 2t squared plus 2t, which ends up being 3t squared plus e to the 3t plus 2t. Okay? And this is what we are going to integrate. So our line integral becomes the integral from 0 to t of 3t squared plus e to the 3t plus 2t dt, which is integrate t cubed plus 1/3 e to the 3t plus t squared from 0 to 2, which is 1/3 times e to the 6th plus 35. Any questions? Next one. Alright, so we need a little C below here. We have our R of t, we have our range of values for t, and we have the vector field. So let's start. First thing, find R prime of t. And I like to use my angle brackets instead of the I and J's. Alright? Alright, so what's that? 2t minus 3t squared. Now, find f of R of t. Good. So the first component is x squared y cubed. So x squared from R of t is t to the fourth. Y cubed, y is minus t cubed, right? So y cubed would be minus t to the ninth. Okay, and then the second component is minus y, so that's just t cubed, times square root x, which is t. So this becomes minus t to the 13th, t to the 4th. Okay, so first step, R prime. Second step, write the function in terms of t. Third step, find the dot product. Okay, so I hope you've seen the steps. Yes, did I make an error?
P to the 4 times negative P to the 9.
T to the 4th times negative t to the 9th is negative t to the 13th. You good? Okay. Let's find the dot product. So you have negative t to the 13th, t to the 4th, dotted with 2t minus 3t squared is minus 2t to the 14th minus 3t to the 6th. Integrate. So t goes from 0 to 1. So we integrate in from 0 to 1, negative 2t to the 14 minus 3t to the 6 dt, which is minus 2 over 15 t to the 15 minus 3 over 7 t to the 7 from 0 to 1, which is minus 59 over 105. Okay. Next one. Put your C again under that integral thing. We have R of t, we have the range of values for t, we have the vector field. Let's do it. First step. R prime, give me R prime. 3t squared, good. Next step, what do I do? F of R of t. So xy is t times t squared, yz is t squared times t cubed, zx is t cubed times t. So this is t cubed, t to the 5th, t to the 4th, dot product, t cubed, t to the 5th, t to the 4th, dotted with 1, 2t, 3t squared. This is t cubed plus 2t to the 6 plus 3t to the 6, which is t cubed plus 5t to the 6. Okay, let's integrate. The integral from 0 to 1 of t cubed plus 5t to the 6th dt is equal to t to the 4th over 4 plus 5 over 7 t to the 7th from 0 to 1, and we get 27 over 28. Is it your turn now? Do it. Okay. Can you give me r prime of t, please? What's that? 40 cubed, 3t squared. Somebody else give me f of r of t, please. 11t to the 7th, correct. Is it 9t to the 5th? It's 3 times y squared. 3t to the 5th? To 6, good. Dot product now. Dot 40t cubed, 3t squared. What is the dot product? 484t to the 10th, plus 9t to the 8th, great. Integrate. What is the integral, please? What's the, when you evaluate, what do you get? Very good. Final answer, 45. Well done.